So this lecture is last but one. So the next week we are meeting the last time. And please concentrate, because today I will be giving the introduction to a method to which I will be asking you to implement the actual solver. So today will be like a smooth introduction to what is the origin, what is the background of the method, and what is the sense of doing that. And the next week we will be talking strictly about the Lattice Boltzmann method itself and about the very specific variant of the Lattice Boltzmann, LBM Tau 1, which I want you to implement. And as I told you, it's not impossible task. I don't give you something you have to discover. You will be given algorithm, you will be given all the knowledge needed to implement it, because I want you to become a little bit practical in those things. But I want you to understand as well. So that's the reason we will be talking today and next week very much about the origin and about how those methods were discovered and what are the possibilities of those methods. And you will be amazed. How is it that possible that such a simple approach gives you actually solutions to Navier-Stokes? And to give you a broader perspective, all that we were talking about last three meetings is still in value, because first of all, we will be solving Navier-Stokes equations again, but not directly, not by using numerical methods of integration of Navier-Stokes. This you can learn from books as well, no problem. Now you are prepared. But you will be also given a task to work with a proper Navier-Stokes solver, but you will not implement it. You will use an external software for that, and this we will do during the labs, okay? So now let's move on and start with the how to say mesoscopic methods, okay? And to introduce Lattice Boltzmann, I need to start from the very beginning, and these are cellular automata, and we will go from this direction. Lattice Boltzmann can be derived from two ways. One is directly from the Boltzmann transport equation, through showing that those equations leads you to the Lattice Boltzmann method itself, or as historically it was done, from the cellular automata. So let's go from the cellular automata. That's the most smooth way. So we will be talking about the methods that are capable of doing such things like this. So this is a flow done by someone from the internet, Lucas Campos. And this is the vortex karma street, so the phenomena that we were talking about, using the methods that I will be showing you today. So after today's class, you should be able to understand or even implement such a solution. And believe me or not, but this is the solution to Navier-Stokes. And yeah, let's move on. This one was done on CUDA. Why do we talk about those methods itself anyway? So the reason for that is that the Lattice Gas Automata, the one that we'll be talking about, is somewhere in between of the zoo of CFD methods. So what you see here on the picture is like a broad scope of numerical algorithms or approaches to solve Navier-Stokes equations. There was a question, yes?
Yeah, I have a question. Those methods that are are they for a very specific equation cases, or it's like implementing everyone and expect somewhat of the same result?
Okay, very good question. That's a hard question, because those methods are put here from different perspectives. For instance, those at the very beginning are numerical methods to integrate Navier-Stokes equations directly. Methods from the very bottom, like from microscale, molecular dynamics, as you probably know, as physicists that work with with the simulations methods as well at some levels, they can be used both for the solid state physics, for atom surfaces, for the simulations of atom systems, as well as fluids. So you can solve Navier-Stokes, but then you have to use a lot of atoms, a lot of particles with this. But here you directly integrate. So it's not an easy question. I would say yes, on the very top, those macroscopic approach is very much about integrating the equation. And what you put into equation is up to you, because for the Navier-Stokes, I didn't tell you much about it, but you can also add temperature term, you can use some other forces, yes? So the equation, the form of equation may change according to application, and then you basically integrate more complex equations. So it's not like directly for one single equation, no. It's very more general. Those methods are more general. And yeah, so now we will be talking about those, not about all of them, but to give you the perspective, the reason for having such a lot of approaches for CFD, because those are used in CFD world very often, is that there was a question last week, and that's why I like this papers to get with the questions from you. And I will give you because I forgot to do it at the beginning. So there was a question about why don't we compare the continuity equation to momentum equation directly and solve this. The reason is very simple, and it comes from the simple algebra, because for the equation that has two unknowns, you have to have two equations. Because if you have velocity and pressure, you cannot compare and solve for both. You have to do it simultaneously. And that I move to ask the question. Someone was asking. Ask anonymous questions. That's an idea for the lecture. I give people the paper and they can ask questions directly during the lecture. So you are only just I'm finished the lecture. If you don't put any questions, there's no problem. It can be empty. Just put it there at the end. Okay, so let's go. Move on, because I can talk hours on all of them. I'm not a specialist in each of them. Those are standard numerical methods that you can learn on numerical courses. For instance, very often we start with finite difference methods. That's a very simple approach in which you directly present your derivatives in form of finite difference equivalence on the grid. Finite volume is a similar approach, but here the equation is presented in the integral form, not in the derivative form. Finite element method, similarly, you have to put special functions that describe your solution, and so on and so on. I will not go directly. Spectral element methods are methods used very often for turbulent effects and turbulent flows. And okay, more and more here we have vorticity string function, the one we talked a little bit last week. Particle in cell. Now, what is the direction here? Okay, with the dots, from dot to dot, we go from the description of the fluid in form of continuous equation into the description. Now let's go from the bottom by single particles. Now, one may ask, so okay, if I have particles like hydrogen, oxygen, we bond them with forces and so on. Can we simulate fluids using approach from molecular dynamics? The answer is yes, because if you know the basic forces and you have many particles, so by the scale of the system, you can solve continuous equation, no problem. You can have the same physical effects in flows using molecular dynamics, but there is a problem and limitation. The problem is obviously the computational power. And if we had unlimited computers, we would be able to simulate by using simple forces and Newton laws for the equations of motion of particles, and that would work in the classical world. We know how it works. Yeah, but obviously we cannot do it. And let's not go into that. The solution to that is to use statistics. And this is where the Boltzmann comes, because he described the system of particles by using special functions of probabilities and the special equations of the evolution of such functions. And this is where the Lattice Boltzmann comes. But the Lattice Boltzmann was not invented by Boltzmann directly. The invention of the methods, Lattice Boltzmann method, was more smooth. So basically, in molecular dynamics, you have particles that can travel in each direction with the with momentum that is from the continuous angle. And people found out at some point that in physics you can solve partial differential equations using methods called cellular automata. And one example of such cellular automata is Lattice Gas Automata, LGA, and this is what we'll be talking today about the simplest HPP and FHP. And from this cellular automata, there is a one single step that leads you to Lattice Boltzmann. And today, the message of this lecture, and I hope to convey it, is to first of all let you understand very easy model in physics of Lattice Gas Automata. This is really very simple, and let's do it today. Convince you that it has capabilities that it has. So I will show you basically examples. I will not prove mathematically. I don't know if there is this is simple or not. There is a PRL paper in which they state this FHP solves Navier-Stokes, and then give you a single message how to move from Lattice Boltzmann to Lattice, from Lattice Automata to Lattice Boltzmann. We will not touch those methods, even though they are interested, not today. Vortex in cell, this is a method in which you have a grid and you describe vortices directly. Dissipative particle dynamics and smooth particle hydrodynamics, those are based on particles that are moving in a free space without any grid. These are called meshless methods. And the material point method, very interesting. By the way, used, for example, in Frozen movie to simulate snow. And that's pretty interesting. So the material point method, someone is interested, I have a paper on that. Not myself, but I mean, someone wrote it from Disney. And the particle in cell, very interesting, similar to marker in cell that we were talking about. Okay, let's move on. Now, FHP. Why do we? So that's just a motivation to get vortices in the flow. And as you know, one of the examples is Jupiter vortex, and there are many vortices on the surface of this planet, and it's very interesting. But let's move on. Challenges from NASA, one can see, to discover vortices and so on and so on. I don't know why do I put so many astrophysical phenomena there. Because there was a task last week to make vortices using LBM tau1, but your task will be different. Let's move on. So yeah, we start with the Navier-Stokes and molecular dynamics. Navier-Stokes you already know. That's why I skip it. I want to move faster because otherwise I will spend 5 slides. Let's think of models that start with those particles that move with the momentum of any angle. And I don't know if someone of you have been working with the molecular dynamics methods, but they are very simple in the principles, because if you know forces that act between particles, and then you can basically integrate the equations of motion. And those forces for atoms and for particles are described by potentials. So if you know potential between hydrogen and hydrogen, between the oxygen and hydrogen, and so on, then you can basically put those forces all together with the equations of motion, integrate with some numerical methods, and move particles from step to step. That's, of course, in details not that simple, but it is pretty much understandable. You don't have an equation like Navier-Stokes, because Navier-Stokes is an equation which, in general, describes a huge system of such particles that basically interact with some interactions. So there are two ways of describing the physical system from the macroscopic point of view. Again, so we have an equation for the velocity in this. So this is like Eulerian approach, and more like Lagrangian approach, in which you have the single particles that move around. Okay, that's I know I oversimplify the whole physical picture of it, but I want to give you the perspective, because today we go from the bottom, and we will be talking about the Lattice Gas Automata. Okay. Now, applications come first. So I'll show you the application of such a particle-based FHP model, one of the Lattice Gas Automata, and this goes back to the project that I was doing with bricks. And why bricks? So no, I was not interested very much originally in the application, but the application came when I started working with the model. So I was given a project in which we used FHP, so the Lattice Gas Automata, for an application in building materials, where the idea was to follow the phenomena of wetting of the brick material. So brick is basically porous material, and it has a lot of holes. You don't see them normally. Usually when you take a brick, you think it's solid, but it's not. There is a lot of holes, and there is a transport of gas, of fluid in the brick. And the way it is transported is obviously not very simple, because there is a wetting, there is a advective transport, and so on. But that was one of the first work of ourselves in the CFD area. And yeah, more technically, this is fired clay brick that we were working with. And we were interested in saturation phenomena. And the idea came from this paper. There was an experimental work in which Polish scientist Jacek Milczarek and with collaborator have been studying the neutron radiography of the saturation process. Why neutron radiography? Because that was an experimental technique that allowed to basically see a water that is propagating through the brick, which is usually not very simple, because how to have a look into the brick, that's very complex. Yeah? You have to, I don't know, cut it or something. Yeah, anyway, there are some experimental results in the paper. Let's not talk much about the neutron radiography technique itself, but there is a radiogram that shows you the container of water. There is an empty container, and there are bricks, okay? Parts of bricks, 10 millimeters, and there is a current of water that propagates from left to the right. And obviously, it's not the picture that we are interested in, but the profiles of this water. So usually there is like an optical density. So basically, from the picture, the density is taken, and the water front is propagating with some velocity. And the whole idea of the project was that we are interested in how these profiles are moving, whether this is diffusion or something else. And the idea was not ours, because there were papers that were trying to study this phenomena, and they claimed that because those profiles do not collapse into the one profile, this scaling with the exponent 1/2 gives the explanation. I mean, they explained that there is some kind of anomalous diffusion, because that's in physics, in the transport phenomena. Anomalous diffusion is one of the holy grail. People looking for that. People try to analyze systems in terms of anomalous diffusion, because usually diffusion, if that was the normal diffusion, all those curves would collapse into one if you scaled the distance. But here, this was not the case. So obviously, you could make it working with proper exponents here. That each of the curves has different exponent. But yeah, so there was the idea of Kens and Lavallée, that they took the same from the similar calculations, but they added the profiles from the model, and they said that this is kind of super diffusion. Super diffusion means faster than usual diffusion. Yeah, so what we did with Zbigniew Koza, we took and now because I don't want to introduce the model itself without giving you the proper motivation. So now I show you how we did it, and then we go into details of FHP. Don't worry, I will do it. It's not like I want to just talk about the paper. Okay, so what we did, we took a model, hydrodynamical model of FHP. FHP means Lattice Gas Automata of Frisch-Haslacher-Poumon. And we wanted to study the concentration from dynamics. So we basically took some kind of concentration of water on the left-hand side. That was C1. the concentration on the right-hand side, similar to this experiment. And we basically run the system, but not like a free flow, but we put some kind of scatterers in the flow. Those scatterers were to mimic the porous medium. Like if you put more of them, then there would be more drag, yeah, so that would be more dense. Those scatterers are acting like solid points that are fixed in the space. So basically, if particle flows into such a scatterer, it will be bounced back or something like this. Okay, very simple model. And for this, we extended the standard FHP5, the simplest possible rules for Lattice Gas Automata, because for us, it was not interesting the actual properties of the fluids itself, we were interested in the dynamics. So you basically, so what is the model? The model is very simple. You have particles on hexagonal grids. So you have a grid of these elements, and so how to create such a grid? You basically take a normal regular grid and you move by half each of the let's say even rows. Yeah, you move by half, and then you get the proper hexagonal grid. So this is moved by half of the distance of those two to the right. Yeah. So how to implement? If someone is implementing, you basically keep it in normal grid, and you just remember that those are moved. Yeah. So you need to remember what is the neighborhood of this. So this is always implemented, very often implemented in the structure you are working. Okay. And there are two collision rules. If two particles are approaching the same node, then one of them stays in the row and one is moving. And there, immediately the physicist would say that the momentum is not conserved, and this is right. But the thing is that in case of this, that would happen if one particle is colliding with one which is staying in the node. Then those two will be moving away. So they will gain momentum, they will lose momentum. So in principle, momentum locally will not be conserved, but in the whole system where there is a lot of collisions, in average, you get the momentum conserved. So that's not a problem. And you have two steps, propagation and collisions. And yeah, basically that's it. So you follow, we'll go into details from the very ground in the moment, but let's move on. You also have those scatterers that we put into our model, and it's pretty simple. If you have a scatterer that goes from this direction, then it will be bounced back like this. If it goes from this direction, it will be bounced back like this. Okay, so there is scatterers can be artificially just spread it around to keep the to give some kind of the drag. And there are results. So you basically run the system. You have a lot of those particles on the left-hand side. They are like concentration 0. I don't remember 6 or 7, something like this. We could change it obviously. So it will start to propagate. And yeah, it turned out that the model works pretty well. I mean, you see this spreading. You can see the effect similar to the experiment. We obviously are not interested in comparison one-to-one. There is like too little. There were too little data, but what we wanted to do was to analyze this not in terms of the diffusion. That was the key, not the modeling itself. So you have to keep in mind what you do when you work on such a phenomena, because if I wanted to do it one-to-one, the goal would be totally different. Our goal was to study such a propagation and then see the same effect, that this is over diffusion, that this is something faster, and then make some kind of theory. What is the idea? What happened? So we basically you scale by x to the power t to the power minus half. Then you see that this goes faster, and now the analysis started in this model. I didn't tell you because, of course, we were trying to how to say, to question or to argue with one of the papers that analyzed, and they used the same model, LGA. The idea was that we have another idea how to explain it. So we got actually the same results like in the previous paper of Kunz and Lavalley. That's why we put their names in the title of the paper. And yeah, now I shortcut a bit of the analysis, but the whole So you are welcome to read the paper, of course, and read how we analyze this. Just a discussion that I skipped because one has to read and carefully think of it. But the solution was like that. Those particles that are traveling in the whole domain, like in the fluid, the other particles that collide, because we need to think in terms of particles. Fluid is just a dense system of particles that has this structure that has the different physical phenomena. There is not only diffusion, there is a diffusion with the velocity of particles. There is kind of advection in the flow. It's pretty obvious today for me, but it was not when we were studying this. We just didn't know why this does not really give the diffusion, because usually there is just a concentration gradient. You have a model in which you have concentration gradient, you solve the equation of motion and you get something faster. So everyone was putting those exponents that were faster, but we did not. We put something else. Imagine that this system is hydrodynamic model, because we are solving FHP, so you got hydrodynamics. So if you have the density difference, C1 to C2, there is difference. So those particles may travel faster because of some kind of advection that is emerged from the diffusion, from the concentration gradient. That means if we take a frame in which we will move with some constant velocity, not changing, it cannot change because there is no force, there is only diffusion, there is only concentration gradient. If you take some velocity and you move with this constant velocity in the direction of the transport, then you can analyze the same system in terms of the diffusion. That was actually something we did with Zbigniew together, because he was a specialist in diffusion and he somehow wanted to understand what happens. And we did it. We took some velocity and we just moved with this constant velocity, and it turned out this is the right proper diffusion plus some constant velocity, and that's it. It's turned out that we can have all those collapsing. There is some little change, but we made quite a long proper scaling. By the way, this one, which is faster, I know you don't like it, me neither, but this is one of the first steps. Yeah, this is just a rapid start, and then all of them collapse to one curve. Yeah, of them are here. The one which is this is just a start, and then they all collapse here. And we just did. So then we did more analysis, but we finished this branch because then I became interested in Lattice Boltzmann, and I want to let you know why. So yeah, this is actually again going from here to higher, and the higher will be now to understand the Lattice Gas Automata. So let's start with HPP gas model in more details. So imagine you have a system which is a fluid, which is a gas or a dense gas, water. And because, as you know, if you have a gas and you compress, then you get water. And so what is this actually? Physically, this is a gas of interacting particles. They have, there are, of course, mass and momentum conservation laws involved, and there are collisions. Particles which approach each other, they can collide because of the forces between them. Yeah, those forces make them to collide like a billiard balls. But so you can approximate this movement and these collisions. So the whole idea of cellular automata, which is the ground for those simple hydrodynamical models of lattice gases, are coming from observation that a system can emerge quite interesting behavior from very simple rules. As you probably know, if you don't, and if you are interested, then I have a course on the modeling where cellular automata are very widely covered for the students, which is next semester. And if you want, you can come. You can maybe assign, I don't know, but you can always come for the lectures where we study such a system like this one. You probably know this is a live cellular automata, one of the most common examples given on each lectures. The amazing thing about this model is that the rules for the behavior of each of the cell that you see here. This is basically the model which describes the behavior of the whole domain at once. So this is the ground idea of the cellular automata, that you have a cell, a grid of cells, and you have some rules that you apply to each of these cells at once. You basically apply the algorithm to each of the cells. And the algorithm for this is very simple. You have 0, 1 cells, and you count the neighbors. If the neighbors are like 2 or 3, then this cell will survive. If the neighbors are larger, then because of the overpopulation, it dies. If the cell is alone, it can die as well. But because of those simple rules, there is like a continuous system which is producing gliders like this, for instance. And there are thousands of interesting systems and configurations that people study. I will not go more into game of life, but this gives you some like thinking of cellular automata itself. People use it for different things, and you can even simulate sand, for instance, with cellular automata and so on. And this obviously is a very interesting topic, but let's move on into our physical world and fluids. And one of the first papers on using cellular automata for fluids is HPP model introducing paper, physical review A, Hardy, Pazzi, and Pomot. I don't know my pronunciation of French, but I try my best. See, that's it. Anyway, HPP because of the names. And this paper shows you the study of dynamics of discrete two-dimensional system of classical particles. In this model, dynamics and computations may be done exactly by definition. So we don't have any magic here. We have particles, they move and they collide. They move and they collide. Nothing else. That's simple. And the equilibrium state is investigated, and the Navier-Stokes hydrological equations are derived. So in this particular paper, they show the Navier-Stokes can be derived from this model. Okay, there are two hydrodynamical modes existing in the model, some waves and some kind of vorticity diffusion. In the Navier-Stokes, the transport coefficient, which is given by Green-Kubo formula, yeah, we have specialists here on that, and so on and so on. So basically, this is about the statistics. And interesting, in 2022, the paper had 733 citations, and I always like to go into let's go into the Scholar. And let's find the paper that was molecular dynamics of classical gas. And let's see how many citations it has in 2024. 780. You see, it is still in use. It's amazing. Still in use. People still study this model. So one is welcome, because it's interesting because of the simplicity, probably. I mean, the simplicity of the ground, because simplicity of showing this is Navier-Stokes and calculating Green-Kubo for transport coefficient is something else. This you can do statistically. Anyway, you have a model in which you can code the state of each of the cells. So there is also a little bit of the implementation in the paper, which is interesting because it's physical paper, but they show how to implement it in a efficient way. Today, on today's computers, you can even do it directly. You have grid, particles, I mean, but that would be a waste of resources, even today. The easiest way is to use the binary system to code in which directions the particles are going in the given scope. So basically, you treat the cell, so each of the cells in your grid is showing how many particles are going outwards from the grid. So you basically have a 0 for 0 particles, 1 for particle coming from to down. Yeah? Down. Then you have 2 particles going to right. You have 3 particles going here and there, and so on. So you can use binary system, which is pretty simple, for instance, for the collisions, because you then just compare numbers. Yeah. If you think in terms of this coding, then you can basically have 4 bits to code each of the cells. So it's very, very like in terms of memory, you can drop down very much. You can use a 4-bit memory for each of the cells. And then there are ways to calculate the operation, for instance, for reversing all velocities. You basically take the operations like this, for instance. So you basically take a Q, so basically take a negative. So negative of 1001, where is 1001? 1001 is reversing the particles would be upward and right. So that would be the negative of this number, which is basically 0110, yeah? Am I right? So where is this? That would be 0110, and this is which one? That should be the right and up, yeah? This 0110, yeah? The last zero is dropped, then you could just see. So basically, you can use such operations, and I will not go into details how they are described, because this you can read and basically study it yourself. For instance, those that will just go, there will be no collision, but those collisions are described. And if you are interested in the review of such, again, more and more details of such cellular automata, then there is a fantastic work from Chopard and Dro. It was studied in my group in years before, because Professor Pękalski was interested in such models. He was actually reviewing the book from Cambridge University Press, Cellular Automata of Physical Systems. There are fluids, but not only fluids. It's fantastic work. I have it on my bookshelf. If someone is interested, well, I'm very much welcome you in my office. Just come in and I will show you. I can even borrow if someone wants, but then I have to put your name on the somewhere, because the people never give back books. But anyway, I have it, and it's really very nice, fantastic work. Not easy to find. If someone finds on the internet the good version, then please let me know. But anyway, let's move on and give you a little bit even more motivation. So what was mentioned in the paper from Haslacher HPP paper was that you can get the sound waves, so basically the density waves. And in fact, it is one of the simplest, the most obvious application of such model, and it works pretty well. If you start with the difference of the density, similar that I did in the paper here, yeah, but there are scatterers that are not visible here. There is just a fluid. Then if you have a density difference large, then you will see that systems relax towards equilibrium, towards the uniform distribution of the density by propagating the wave. And this wave propagation is solving the wave equation. If one wants to study it macroscopically, that's basically wave equation. It is a compressible flow, of course, because we have a compression of gas here. It's like a gas flow. But anyway, this is HPP. So it's like, and it's physical regulators. Amazing. Such a example, yeah? One can study, 86, yeah? And then people are scaling it using very supercomputers. And for instance, Sachi is a person well known in the Lattice Boltzmann community. He works in Rome. And there is one example, the paper in which they used a supercomputer to study HPP model in a very interesting large phenomena, and they even went into the turbulent effect somewhere, but not with HPP. But anyway, I wanted to just give you some perspective that by scaling you can even get more interesting results, but I will leave the results of this paper for yourself. Let's move on. So to basically think of it, you have to think of how what assumption did we make by moving from the physical system into cellular automata. So first of all, our particles are traveling only in two directions. In HPP, the Y and X components are the only directions of particles. That's the first one. The second, velocities are always one. So basically, each of the particles can move only from one to the neighboring nodes. And the collisions are simplified because of this assumption. Yeah? So there are those two assumptions that you need to think of. And now for the microscopic rules, we select only two collision modes. One of them is that two particles are approaching each other, and then we reflect them by 90 degrees. And this is basically symmetric. Yeah. So those two and those two behave in a similar way, and the ballistic motion. And this defines our algorithm. So the basic HPP implementation would be that we choose the two-dimensional lattice. We have a particle that is coded by 4 bits information. Yeah, this is number from 0 to 16. Okay, and here is an example that such a situation is coded to 11. Such situation is just 2. Such situation is just 4. And now you see the difference of thinking. And this is your choice. If you implement a Lattice Gas Automata, then you have to choose whether, by definition, your particles are approaching the given, at some point, are approaching given node or are going outward from given node. Yeah? In the paper I showed you, it was a bit different. So that's something you need to think when you read the papers, how it was assumed. Whether this has is important or not, that depends on the main implementation. Now we go deeper and deeper into the technical part, how to implement it. So you basically have a collision step, which is negative. That's pretty interesting. But by definition, we did a system in which you take the negative, and this is the collision. And then translation step, which basically after the collision takes those particles and move into the nodes that are pointed into. And how to do the translation step easily, having coded it into the binary system of such numbers, you can in a clever way use the simple logical operations, and you basically take a logical operation with each of the neighbors, and you take particles that are traveling into your direction, and you copy them into the direction to the next cell. You get it? It's really like just taking the numbers and with some proper flags. Okay, and what you get is solutions like this. These are again solutions from the previous years of our students, because our students were working with such systems, but I also find some nice. So previously it was the density wave, but here is something more interesting. Is like a gas going through a hole like that. You can even take some averages over spatial part of the system and get velocity fields. So you see there are some vortices traveling in the flow. And yeah, of course, as you see, it's pretty nice, it works, but honestly, if you want to compare this to the real world situation, it won't be that easy, but it does not mean that it's not working. Here is actually HPP model on CUDA, so the person was working with to actually optimize it. But let's not now move on, because the model is very simple. I don't know if you've seen the problems here, but this is not really circular. Probably this is like you see it's kind of not simple. I will not now describe more of the problems here, but there is a problem of symmetry, and people found out that by changing from the rectangular to hexagonal grid, you get much better results. Now, this is an example of HPP again, so just transport of gas, and the obvious problem that you see is just that there is no like vertical movement until this jet of gas will hit the wall. But if it hits the wall, by definition of this of those collisions, the gas will go down, then left, and there is some kind of dispersion here, but this is very little. And the problem is, of course, that you see all those directions in the flow. And just by changing into the hexagonal grid, you solve much of the problems. Yeah? These are problems. These are again the HPP results, because I like those models and I like to play with them. They are very interesting. Again, at some point they mix together, and there is this equilibrium state of a constant density everywhere. But the way it goes, it's okay. It's like a strong jet of gas put into the system. I wouldn't say you can see a fluid here, But yeah, again, you can play with many situations here, but the most interesting is the porous one. I will show you. Okay, there is such a thing like this with small holes. Okay, you have an obstacle like this, so you can put an obstacle into the system. Here we would expect something more like a vortex Kármán, but it's not even in the gas. Yeah, so you see it's very pretty awkward. This is actually interesting. It goes like that, and then I put even the porous medium here. I was interested in how it will behave with porous domain like that. So you can see it is like the transport is there, the diffusion is happening in this macroscopic world, but it was not the way. So now HPP, electromagnetism. People are doing so. Just to mention the paper, the problem with symmetry is visible, yeah, and okay, and FHP. So then in '86 again, there was a paper from Frisch, Haslacher, Pomov, who immediately did this change from the rectangular towards hexagonal grid and showed that the problems of those symmetries are solved. And that was we showed that class of deterministic lattice gas with discrete Boolean elements simulates the Navier-Stokes equation, can be used to design simple, massively parallel computing machines. Now it has 4,078 simulations. It's let's see again. That is the Frisch, Haslacher, Pomov. No, I of course put it wrong. Lattice Gas Automata for Navier-Stokes. Again. Lattice Gas Automata for Navier-Stokes. So how many it has in 2000? Is there this one? Lattice Gas Automata for Navier-Stokes. Okay, no, this is the book. Okay, this is the task for you. We'll not spend more time. How many citations it has in 2024, but it goes. Pretty interesting, 4,000. It's physical review letters. Very nice work that started a lot of research because they basically by changing this, they had to also put a lot of additional analysis of additional of the complexity that this change brought, because by changing the structure of the grid, you obviously have more complex way that particles can approach the given site, and then you have more collisions. And by changing a set of collision, you can, for instance, change the viscosity of the system. So if you want to numerically simulate a fluid, what you have to do, you have to take another set of the collision, because the collisions can be treated in different way. For instance, you can take only binary collisions. So as it was in the HPP, we had only one collision and the second with two particles. If there were three particles approaching one side, nothing would happen. They would just go like that. Yeah, there would be no change. But in FHP, it is even more complex because you have 6 directions from which the particle can come. And then you have to either consider only binary collisions or also collisions of 3 particles. If they are like going like this, the question is if there will be a collision or not. And there is no single answer because it depends on what you want to study. And so then from in this community or in this research, FHP or Lattice Gas Automata became models which are divided to some classes, like Lattice Gas Automata 1, 2, 3, 4, 5, 1, 2, 3, 5, 4. Yeah, 4 was there as well. But anyway, the most known is FHP3, which basically is a model which simulates the fluids up to some viscosity. I was studying FHP5, which was the simplest possible collisions, because I was not interested in the viscosity of the flow. I was interested in the dynamics of a system which is over diffusion. Yeah, that was the idea. And okay, so basically we start with the triangular lattice. This is directly from the parallel paper. It shows the particles that travel into the given site. Okay? And 2 probably means, I don't know what this means, but Okay, particles at time t and t+1 are marked by single and double arrows respectively. So that means there is particle traveling in this direction. So in time that t+1, it will travel outward from this grid point. So we basically see the situation before the after collision, because this is the particle that will travel. It travels, and now this particle is before the collision, so the collision has to be resolved. Then the whole algorithm has two parts. The first of all is the traveling, and then the collision. So for instance, where the collision will happen up here. So you have a particle travels in this, and this direction. Here the collision is very simple because it will just reflect. Okay, but details are given in many papers, and that was already discussed. And as I said, the FHP model is vary, and the collision terms affect viscosity. Okay, there are some papers I mentioned. The slides are for you, of course, so you can see. And depends on the source, of course, as usual. The problem is not to find the information. The problem is to select the proper one. I give you some sources of nice tables where you can find basically table for given viscosities and the FHP models, because they became quite complex in terms of the. So if you wanted to do it by yourself, all the collisions, you would spend a lot of time. What you can do, you can use special tables of collisions not given FHP models, because for the FHP3, there can be 76 collisions to be resolved. So you need to know the way they are resolved is very simple. These are like lookup tables that for a given number in a given node, you basically get another number, which gives you the situation after collision. So it's very simple in implementation if you do it properly. Because if you do it like, okay, I have particles, so I put those particles here, so I have X, Y, Z. No, that's not the way. You have to, the best for me is the code by numbers. So basically this can be also number, but not 4 bits, but 6 bits, yeah? Because it's the batches. Okay, so so there are some papers that I can mention. There are also possibilities that are stochastic, so you can choose the collision with a given probability. That actually gives a lot of input into the model, because it becomes not deterministic anymore. So FHP can become like the model in which the situation like this is resolved in different ways. Yeah, it can be with some probability, have the different situation. Yeah, there are like you see, there is a particle going here, there, and there is one which is resting. It can be it can go into different situations afterwards. What is interesting to consider are boundaries. You've seen in my movie that I had a boundary from which the particle can be reflected, and this is done in the most straightforward way in cellular automata, because you basically have to assume some kind of boundary condition. For instance, here is the no-slip condition, so if there is an in-state and there is a wall, then the velocity is basically reflected. And if you do this, then you get the zero velocity on the wall, and this is the hydrodynamically no-slip condition. Okay, and then you can get okay. There is the density wave in the FHP model. Okay, this is HPP gas. You see the symmetry problem. I even calculated this using the very large system. It was 2000, so it's like 4K with many particles. This is HPP. You see what happens? This is non-symmetric. Now, do I have the same for HPP? Yeah, I have a comparison. There is an HPP and FHP. This is the HPP, and this is FHP3. It's from the master science work of our student Sebastian Szczecina from our group. In 2008, he was considering the FHP3, and you see the circle and you see the quad. Yeah. So this is the difference, and the only is that you choose the right grid. Yeah. And the collisions, of course. Yeah. Okay. Now this. Why do I have so many of those? Okay, but because they look more and more like fluid. This you already seen. I will skip it, and now some implementations and challenges. This is one of the challenges that I will give to someone who wants to know the FHP and cellular automata to get a proper Reynolds number flow with the cellular automata. This particular example is a two-dimensional flow over a plate. So you have an obstacle, you have an inflow, you have FHP model, and what you can see are the results of vortex Karman strip by using FHP model with the Reynolds number 70. Challenge, of course, would be to, first of all, compare this to the literature, because it's a time-dependent flow, it's pretty tough. And how did they get the velocities here? It's not like this is one of the cells of the LHP model. No, each of the velocities is taken by averaging over the spatial distance. So you have some kind of like rectangle, and you have hundreds of those particles that are traveling with those 6 velocities, and you take spatial average. You can also take an average in time, and then you get a velocity which is small, and then you can basically see the macroscopic solution. Okay, this is one of the challenging flows. The other is driven cavity. That was actually given by myself to my student. But the idea still would be to make it proper for the proper Reynolds numbers with FHP. It's still challenging. You can see papers even today that are appearing in papers. So basically getting those vortices and so on is not that simple. And yeah, there are many ways to implement. We had our students very often use collision tables. But there can be also equations for dynamics of the model. This is in the book of Chopard and Draw. Sometimes when I have more time, I can even write on the blackboard the equations for it, because they are very interesting, because the collision rules can be implemented as equations of the FHP model, but this you can read in the paper, yeah, that you put okay. But this I recommend the paper from Cambridge I told you, okay, for the another way. Now, how to get the solution like it was in this figure, like this one, or how to get such velocity fields from the cellular automata model. For this, we take averages. Basically, for instance, if you want to get the probability of particle traveling in a given way, you can basically take the number of particles in a given space in a given time and take averages. You can average in time. This is a smoothing procedure. From that, you can get the density. So basically get the density in a given lattice node, or even you can get the momentum. So basically take the I is denoting the directions of in the lattice, yes? So if you have a hexagonal lattice, you have 6 here. And then those two are basically the solutions of the system. Now the practical questions are: if you want to do vortex Karman or even Poisson flow, the simple flow in the channel, then you need to have really quite a lot of grid points. Here for the vortex Karman, it was like 300 by 60. That is the typical size you need. It's not that much, but yeah, if you want to do it proper for high Reynolds number, then you need to scale it up. And for the visualization, I recommend, if someone wants to work with such, I will tell more in the Lattice Boltzmann part, but to export the velocity or momentum profile into the so-called VTK file. VTK is very simple. It's an ASCII file you can use for that. And then you basically write down the dimension of the system, you write down the velocities one by one from the entire grid, and then you can import into the proper visualization toolkit. For here, I wouldn't recommend open frameworks. I would more recommend ParaView program, but this will come later on the lab, because this is very practical. Okay, what you can get, this is the example of diffusing process with FHP5, but I will not play it here. I want to discuss more about why do we want to go into the Lattice Boltzmann. So the cellular automata are deterministic by definition, but FHP go a little bit beyond, because gives you the collision rules are kind of leads to non-deterministic behavior. That's what we see here. It can be implemented in deterministic way, and there is again Chopard and Tropo, which introduces the deterministic way of implementing the FHP model. But I will not go into that deep details of the modeling here. People are using the model in different areas of research and for different interesting applications. For instance, there are people interested in creating FPGA processors that are directly solving Lattice Gas Automata models on the chip. That means you can do it very fast. You can skip this programming part, and it goes directly in the processor. So basically, the algorithm is such simple that it was possible to solve Navier-Stokes directly on the chip. That's pretty interesting. There is even probably, yeah, there are some, I will just show it. No, I will not show because I have it, but not here. But there is a video in which you have the propagation of this, but okay, it's hard to understand if you think only on the application, but the way it's working is unique because this solution happens on in the computer chip itself. There is no program involved. Okay, but let's go down deeper and deeper about applications of FHP. There are applications of FHP that we used for comparing into the microchannel flow, because the FHP is, we wanted to check, okay, that's about the microchannel flow project. In this project, we wanted to check whether FHP is capable of calculating a real flow and compare this directly to the experiment. So microchannel flows are important for applications such as chemistry, because we have a microchip in which there are some channels, okay, and the fluid can go through, so it's like a porous medium, but it's in micro scale. So there are some, so you can basically make it very, very tiny. And we wanted to compare to the experiment this FHP solution so that we can benchmark such a unique model in a proper like fluid system. And there was a lot of problems with the visualization experiment, and we used micro PIV technique for the experiment. That was a project I was involved in when I was on postdoc in Bremen, and the idea was the following. So you have an inflow on the left-hand side. There is a pump that is pushing the fluid through the channel, and obviously because of the fluid mechanics, you have a profile of so-called quasi profile on the inlet, and then there is a kind of microchip through which the fluid will go through in the middle, which is very tiny, and there is an outflow, so the fluid will go like this, okay? And the idea was to study what happens in this microchip by using experiment and FHP. And there are experimental results. These are results from micro PIV technique. Just roughly tell you about it because it's interesting. You want to study CFD, you need to know how people do it experimentally, because sometimes you need to compare. So for instance, now we are starting and establishing a contact with a group from Wrocław, from Politechnika Wrocławska, that are studying fluids using PIV systems, not micro, but PIV, so large ones. This was like small one in the laboratory because the professor in Bremen bought a very nice instrument for that, and they wanted to study microchips. And it worked. So we basically have a fluid here, and the fluid is supplemented with markers, with special particles that are glowing under the laser light. Okay, if you have a laser, but this has to be a laser that is not like a point laser, but it's like a like a paper like this. Yeah. So you have a area of a laser that you are cutting the system, and basically, if you blow it, you can see that those particles, if you light it, you see that those particles that flow in the with the fluid are advected, and you just see those particles. You don't see the fluid itself. It's hard to explain on this particular case, but the output of the experimental setup is that you see particles picture by picture how particles are moving. And there is a special software that by having this animation of particles can derive the velocity fields. So it sounds very simple, but they spent almost half a year to run the system because there is a lot of problems. Imagine from experimental point of view, they cannot study many of those systems because particles affected here can, for instance, stuck to the obstacles, yes, because of the physical and chemical properties of those particles and the material that was in the flow. Particles can even stuck or even fill it such that it becomes a different kind of configuration. So therefore, numerical methods are important because then you can study more and estimate what. So to produce such chip in micro scale, it was 2,000 euro. And then imagine you do it in the wrong way. So they wanted to create a numerical procedure to first check it and then buy the microchip. That was one of the motivations. So yeah, to make the story short, the whole project was also about to give Sebastian, our student, a proper motivation to work, and he was studying FHP model. We did, of course, Lattice Boltzmann later as well for that, and we basically continued the project, but the experimental part was finished at some point because of the problems with the experimental setups of those microchips. But anyway, at some point we compared micro PID with the FHP, and the comparison by visual comparison is here. You can, of course, take some plots and some more rigorous comparison, but here you can basically see that those channels that are visible in the PID are also visible in the FHP solution. So basically, those channeling effect is very similar. So basically, for instance, here you don't see a transport through this channel. Yeah? This is what you should look for. Here, neither. There is a really very like sparse number of, low number of streamlines. That means there is almost no transport. The whole transport goes like this, and here as well. Yeah, it sounds maybe pretty obvious because it's a very small system, but imagine doing that in large porous medium. Huh? The idea is that you take this and then extrapolate towards something more complex. Yeah. So basically, it was pretty successful. You can see the x direction here. You see the very large velocity here, and this you can see as the more dense PID result. Yeah, okay, it could be done even better and so on, but that was the project. Then we had students who did FHP and okay, that was still Sebastian, but we had more. Okay, there is an example how FHP works in on the grid, so you can see even visualization of those particles in time that they change and they basically are traveling. This is what is inside of the model, but this is not exactly what we are interested in. We are interested in the FHP as a flow solver, and one of the particular examples is the work of quite famous people from Polish physics, from Mark Cieplak, Renata Rybka from Polish Academy of Science. And they were working on the cellular automata studies of circular Couette flows. These are flows in, you remember Couette flow? That was a flow in which the top wall was moving. I was showing you the analytical solution for that. And the bottom one was no slip. And we had the viscosity effect that there was a linear flow. What they did, they were using a similar system, but the system was circular, so the outward wall was rotating, and I mean not the whole system was rotating, and this was again interesting system, but they got a chaotic behavior, so kind of turbulent effects. So, for instance, what they had to do, they had to implement curved boundaries into the lattice gas automata. So they basically describe it. You can see in the paper more details. I will not describe them in details because then we will spend the whole day on each of the papers. Really, honestly, these are very complex papers, but about a very simple models. If one is interested in curved boundaries in the FHP, please go on. I'm very open to discuss. That's much likely, but anyway. So they had different situations. For instance, Kawet flow in which the outward wall was moving this or this direction. The Kawet flow in which this was moving in this direction, this in that direction, and so on, with different velocity differences and so on. And they were studying this hydrodynamical system. What happens in the flow if you do like this? And they used FHP for that. That's interesting. Now, nowadays, that was like, anyone. I'm very interested in doing such things, but one has to, like feel it to start studying, because I see you can see more interesting results in the paper. I would actually do this and compare to finite volume methods to the open form. That would be fantastic project to check whether FHP is really capable of doing this properly, because these are chaotic systems. Yeah, so there was an idea that one can compare FHP in these curved boundaries. Okay, very famous paper and very famous people, Rothman and Zaleski. You can see Rothman group on MIT. They used the lattice gas models in many situations, and they used for phase separation. It's interesting because this is about the multi-phase flow. And again, multi-phase is another phenomena. So this is standard vortex Karman. By the way, this is a famous photograph from NASA in which those clouds that are there are showing the vortex Karman street. And how did this happen? Because the whole atmosphere was moving over the island, and this island was creating such a huge phenomena in the large scale. Who knows how the tornado or whatever happens, like maybe originates from such an island somewhere. Okay, this is an example from Rothman Zaleski. By the way, this is similar to this microchip, you remember? And the ADA, and the fluid forced from left to right. And you can basically observe where the fluid goes. This is just one of the applications of lattice gas, but they also use it for two-phase flow. And this is more interesting. You can use water plus air, oil plus water, and so on, and different kind of chemical stuff that is flowing together. And this is 9:30. Yes, am I right? Like, wow. Yeah, I was like 10:30. Okay, immiscible means non-mixing, niemieszający się. Fluid using lattice gas automata. And this is a model which is showing you another perspective to CFD, because now we can have different species. But it's not only about to calculate the flow of two species together, but they also can interact. And yeah, let's now not talk much about details, but about the overall idea of the model. So you basically get two species of particles on the grid. One, let's call it red, one blue, and you have to assume some interaction. So, for instance, the red can be directed towards red. Yeah, so particle can be attracted by itself. So it's kind of chemical reaction, or that the particles can be attracted, and yeah, so there is a maximization of this density. Yeah, and there is a paper color gradient method, and in Review Modern Physics 94, and there are an example of such a phenomena that particles of one kind can group together such that they create stripes and droplets. And those stripes and droplets are created because of this attractive force. So in the fluid, this attraction force can be, for instance, a kind of what keeps the fluid together can be kind of surface tension, for instance, but it can be also chemical reaction. And there is more about it. I won't go much because that would take us a lot of time. But please have a look into the paper of this one, Review Modern Physics. It will collaborate it, okay? And from 94, and then you can be able to do such things. And what I'm interested in is to animate it and to see the dynamics. And this is really very rare because lattice gases were very, there was a dynamic development of those models, but it was at some point stopped because of many reasons. But yeah, there was again anyone. And the idea was to re-implement FHP. There are obviously some ideas for the future works with students at some point, but it's as I said, unless we really want to do that, to render phase separation movie and add the theoretic fluid, for instance, to see the more interesting behavior, and maybe gravity, because that would give you the splash of liquid drop. Because if you had such a situation, and you put a gravity, and for instance, one fluid would be here, and there will be a droplet of the second fluid, you probably would be able to reconstruct the droplet phenomena with this model. If you do add the gravity and do the splash drop. And obviously, the third dimension would be very interesting. Okay, what people also do, they study another kind of systems, for instance, lattice gas automata in phenomena such as the gas, granular flow. So the rest particle is introduced, and there is some kind of energy dissipation in the system. So particles can dissipate energy, so the energy is no longer conserved. There is a temporal side occupation by more than one particle, so particles can group together and they can be in one type, and the particle may move along direction. There is some bonus bike. I don't have figures. Physical Review 94, and maybe I have the paper here. Okay, some basics from those papers from granular flows. And yeah, there are those rest particles introduced. There are different kind of collisions for this system. So there are physical motivations for grouping particles like that. For instance, this situation may become the pile of particles like that. Okay. There is an effect of gravity. Let's not go into that. It's pretty simple. You have a wall from which particle can also bounce the sand particle. Here is one of the results, and these are the density waves in granular media. And these are the waves that are studied in granular matter research. So basically, you have a gravity which is in this direction. So the gravity is that direction. The system is one-dimensional, and you have the situation is like that there is kind of density gradient in the x direction. Sorry, here. The density gradient in x direction. The situation at the beginning is random. So you have random particles of sand. And what happens in sand is a phenomenon. So you can find the PRL papers about what people study that there are density waves emerging in the even one-dimensional system. Even though you start from the random situation and you continue the movement of particles in this x direction, you move in time. This is like the state of the system in time. Yeah. So you have a time evolution of the system. Some density waves are emerging, and these density waves propagate through the system up to some situation in which you have a huge number of particles here and very little number of particles there. Yeah, I may be wrong, which is large, which is low. The important thing is the density wave. How is that important? Do you use a car? If you go to a traffic jam is this situation in which you have a density wave because of some statistical behavior of the whole system. You have a lot of cars which are initially even random, but if there is some critical density of the cars on the road, they will emerge into the traffic jam like this. So some cars will be very dense in one part of the system, and some cars are like sparse, yeah, so they can travel easily or hard. And those models, the one-dimensional models of granular media, are also used in the study of the current traffic jams emergement. Okay, but no strict paper here. But if you're interested, I can find for you, or you can just Google it. Traffic jam with the gas automata. Okay, that was another idea that I want to see this. Okay, in time evolution of that, but not only in 1D, but also in two-dimensional system. That is actually something that no one was trying. I don't know, and try to experiment this in a tube. So you have a tube that has some geometry, which is more would be more interesting, and then see those density waves. Okay, quantum lattice gas automata. That's a I wrote in Polish ciekawostka, so the more for you to attract you into the lattice gas automata world from different perspective. I don't work with quantum effects, but what you see here is the evolution of the wave packet. Okay, so basically you have a time evolution of the wave packet again in time. So it's one-dimensional. Here is the Gaussian, and then it splits into the probability distribution in space. How does it work? What are the rules? How this corresponds to particles on the grid? Please read. But again, the idea here, because very often in physics, this is what people do, is that we have a gas automata that is solving partial differential equations. Now, if you know another kind of equation, you can adopt a model like this to something that has no particles itself. I mean, you know what I mean, yeah? So that's the way the people try to use the lattice gas as well, and maybe that's the approach. So if someone is more into quantum effects, you're welcome. And interestingly, this FHP approach can also give you very physically sound results. This is an example of the instability in physics. So Kevin Helmholtz as instability in fluids, which can be also simulated using the lattice gas. So for instance, here are the examples of another methods or observations of what happens on the border of two phases. So if you have two phase flows and you look deeply into the movement of two flows together of different kinds. They can be of different diffusivity, of different viscosity, or different chemical properties. That's very general. This stability is quite general. It's not about one phenomena. Then you can observe, and here is an example of FHP3 model used for two phase flows. And again, Cambridge University Press in the book of Rivet and Bond, and they used the FHP3 variant, the one I told you about, with some collision terms, and yeah, it works pretty well. Okay, Kevin Helmholtz. Fingering is a phenomenon that happens in porous medium. I will take you 5 minutes more because I started 5 minutes after. I hope you are okay with that. And so we have a fingering effect where the one flow is pushed in the porous medium, and then this multi-phase flow is choosing the different paths, but it's also organized in a way that some kind of fingers are created. That's why it's called fingering flows. You can also see in lattice gas. This on the supercomputer Cray. When I was younger, Cray was the first one in the world. I don't know if it still is called like this, the main supercomputer in the world. But then FHP was also used to study two-dimensional flow on these supercomputers, and they got the vortex Karman and everything. Yeah, quantum mechanics again. There is some kind of I don't know. I will not go this wave packet going through some barrier and so on. They study turbulences. That's interesting. Quite amazing. Turbulence in FHP. This is pretty decaying turbulence. Okay, for one of the papers. And I was actually amazed seeing that in the high resolution lattice gas simulation of two-dimensional turbulence, physical regulator Sachi, I already told you about him, still active professor in Rome. Sachi and Benzi are still working in Rome. They had a grid of 8,000 of nodes, supercomputer, of course, and they got comparison of FHP results to spectral methods. And they compared one to one, so I don't go into details. They claim they have turbulences in FHP. So, okay, summary. FHP has a simplicity, computational speed, but it has noise. I didn't tell you anything about the problem. The problems with FHP is that if you want to make turbulence like this, you have to use huge lattices, not available for the home computer. For normal computers, you need supercomputers, and they are still noisy. The main problem is that you have to average over huge part of the systems to get the proper velocity fields, and also averaging in time is involved, which makes it complex to study. Yeah, so basically that's the main. So it's like with molecular dynamics. If you had a huge computer with huge memory, maybe that's a way to go, but who knows? It is noisy completely. And this is actually, yeah, we need to use large statistical physics. And the statistical physics is like an averaging over time and over space. And this is wonderful result of one of my students in the past, Victoria. And Victoria has done the study of Julian cavity with FHP for different Reynolds number. And she did wonderful work. At this time, I was too young and too little experienced to make a paper out of it. I think it's still there. It's still possible, even with the results from Victoria. Who knows, maybe one day we'll write something. But anyway, what she did was she calculated Julian cavity flows with FHP at quite large grids. It could be larger, as you can see here in the corners. You see something, but it's like almost there, yeah? And compared to the literature data, one-to-one, it was like compared for the same Reynolds numbers. And she observed all the phenomena that we see here was observed by her. It was not perfect. So that's maybe why I didn't decide to start writing something about it, because I was like, why here is like this and here is like that. Yeah? And we see some subtle differences here, but she captured the main vortices, the main differences for Reynolds numbers. Okay, they're slightly different, but yeah, also kind of definition. Okay, let's move on. And now the Lattice Boltzmann model, and that will be the last slide. And next week I will introduce you properly the whole Lattice Boltzmann model from the ground, and you will be prepared because Lattice Boltzmann is even simpler to implement than FHP because of this statistical approach. So the idea, there's one of the like first papers in the community of Lattice Boltzmann. McNamara Zanetti, 88, physical regulator is use of Boltzmann equation to simulate Lattice Gas Automata. So now we connect the particle approach from FHP with statistical physics, and the main change is that instead of particles that are traveling in the grid, we will be using continuous distribution of numbers from 0 to 1. So we will no longer have particles traveling in the grid, but what we will do in the Lattice Boltzmann is to use the probability that there are particles of a given velocity and a given position in the space. And this is the only change. The grid still will be hexagonal. There will be transport and collision term, but the way they will be introduced is they are a lot simpler than in FHP, okay? But in your mind, what has to live, what I want to live after this lecture is this change. We go from Boolean 0 and 1, so particle is there, but there is not, to the continuous number from 0 to 1, which is discretely like distributed over the grid, yeah? And we basically get rid of the problem of averaging. And it's beautiful, because then what you get is all the fluid phenomena in the world. So that's where the CFD world has started using Lattice Boltzmann, because it's very, very simple and gives you everything you need to, I mean, not everything, it's not like state of the art for all the applications again, but it's very useful, robust, like unique in the approach and gives a lot. So that's what we'll be talking about. So yeah, the next lecture next week will be about the Lattice Boltzmann methods. See you next week. Thank you very much. If there are any questions, please, now you can ask, but yeah, we're over the time, so I will just stop it and